So welcome everyone. My name is Tolad Zoru. Today's host for our webinar. First, I'd like to thank you, Dr. Mirjana Povic, for joining us today. I'll let you introduce yourself, Mirjana, but for our audience, I'd like to say there's a question or chat bar you can find where you can forward your questions. After the session, we can proceed to the Q&A part. So Mirjana, the floor is yours.
Thank you very much, Thibault. I just turned off my video. I don't know if you can see me just for a few minutes while I present myself, and then I will turn it off.
All right. Yeah, I can see you.
Okay. So hello, everybody, once again. Salam Nachu. So first, I would really like to give my thanks to Thibault for organizing the webinar and ESSS in general for, as always, really an amazing work that the society is doing. And I saw when COVID started that these virtual webinars started as well. So I was really very happy to see that the motivation is there to, despite whatever situation that we have in Ethiopia, Ethiopian Space Science Society is always there to push the activities related with science and outreach. So when I got the invitation to give a talk, I was really not able to say no. So I'm really happy to be here with all of you. I will very briefly present myself. So I'm assistant professor at Ethiopian Space Science and Technology Institute since basically the establishment of ESSTI. So I had really a privilege to work at the ESSTI from its very beginning and to really see how the ESSTI was growing, and also the astronomy development and space science development in Ethiopia. I also had the privilege to meet more the work of the Ethiopian Space Science Society and also the history of the astronomy and space science development in the country. I'm also associate researcher at the Institute of Astrophysics of Andalusia, where I was working before for about 7 years before I joined the ESSTI. So also I'm full-time based on the ESSTI now in Ethiopia, except now this time of the COVID. I'm still attached to the Institute of Astrophysics of Andalusia, mainly through the research project and also some of the student supervisions that we have. I'm also a honorary lecturer at Barara Space Science and Technology University in Uganda. And my field of research is a bit the one that you will see, that we will speak about here. I think I will now turn off my camera so that we can facilitate the connection. Can you all hear me and see the slides, the first slide?
Yes, it's clear from my side.
Okay, perfect. So the talk that I will be giving here is about active galaxies, and I hope during this talk I will be able to present you a bit what active galaxies are and why they are really so special in the universe, and actually an amazing source of information. So the talk will be divided into two parts. The first one will be just introducing active galaxies in general and seeing how we can really benefit from the research done in the field of active galaxies. And then the second part of the talk, I would like to dedicate a little bit to the projects that we are running in Ethiopia and in East Africa as well, in collaboration with East Africa, some of the projects, so that you can also have a bit the idea about those questions that we still have open in astronomy regarding active galaxies, how from Ethiopia we are also trying to contribute to their answers. So I will now go to the next slide, the very first slide actually. So the very first part will be to see a bit just where we are situated in the universe when we are actually speaking about active galaxies. I know that for some of you, the first few slides that I will go through might be too easy and basic, but I was not sure really what will be the audience, and he would mention that it's from children up to the just adults. So as I said, the first few slides are really very introductory. So just to remind you, when we speak about universe in general, we can divide the universe into different components depending basically on the distance of different celestial sources from us. So basically, if we start from the part of the universe that we know the best, so basically our Earth, and then the solar system, and our sun, we have different parts of astrophysics that are dealing with the research, with studies within these components like solar physics, like planetary sciences. But then once we go out of the solar system, we know that nowadays we are dealing with the detection of many other planetary systems, and we enter actually in the world of the stars that we have, where we have hundreds of billions of stars only in our Milky Way, and then either a bit less or more in other galaxies as well. And we have stellar astronomy that is actually dealing with all issues of the physics behind the stars, what are the properties of the stars, how stars form, how they evolve, and so on. Then we come to, when we go to even bigger scales, we come to our Milky Way that we know that is made of, as I said, a few hundreds of billions of stars, and then dark matter as well, stellar remnants, interstellar gas and dust. And we have actually galactic astronomy that is dealing with the properties of our Milky Way. And then once we go outside of the Milky Way, we find ourselves with really an amazing and very, very diverse world of galaxies. And that's where the extragalactic astronomy comes, where we study the properties of the galaxies and we try to understand some of the questions such as how the galaxies form and also how the galaxies evolved across the universe. And to really understand that, we have to study all different types of galaxies and also all different properties of galaxies, and finally try to make a puzzle for understanding really the formation, evolution of galaxies, and then the evolution of our universe as well. So I will go now to the next slide, and this is one of the slides that I really like to show, because I think it's a bit the beginning of extragalactic astronomy. And here you can see one of the pictures obtained by Hubble Space Telescope in late 90s, when for the very first time astronomers pointed the telescope to one very small part of the sky that previously was thought that there is nothing really there. And people observed for about 10 consecutive days with more than 300 exposures. And finally, we obtained a picture that you can see here in this slide, where astronomers saw that it's not only that the field on the sky that has been observed is not empty, but astronomers were able to obtain, as you can see here, hundreds or thousands of galaxies, and also to see that really the world of galaxies is amazingly diverse. in terms of all different properties. Colors, as you can see here, we have those galaxies that are more blue, those that are more red, yellowish, and so on, in terms of the size, in terms of the shape of the galaxies, and so on. So basically, as I said, this very first observation, deeper universe, we can actually consider as a beginning of really what we call in astronomy deep surveys, and it really brought the revolution in extragalactic astronomy research. So regarding, let me check if I images of Hubble up to nowadays, we actually really had a revolution in our knowledge regarding galaxies. And now the next few slides will just show us how really diverse is the world of galaxies. And then we will a bit situate us to see where we are when we speak about active galaxies. So here, for example, you can see all different types of galaxies in terms of their morphology or shape. So in principle, in astronomy, we have four basic types of galaxies that are elliptical galaxies, like the one here, or lenticular galaxies, such as the one that you can see here, spiral galaxies like this one, or this one, or this one. I hope you can see the cursor on my screen when I'm showing. Can you?
Yes.
Okay, good. So you can see that we have different types of spiral galaxies with all these spiral arms. And then we also have irregular galaxies, such as the one here in the top right part of the screen, or the one that is on the bottom right as well. But also beside these four main types, we have galaxies that we call more peculiar galaxies. So those that have different structures that are not really common, like tails, as in this case here, or different filaments of the gas and dust and star formation going on, like in this case, and so on. So these are some of the different types regarding morphology, but also of property values in terms of luminosities of the galaxies, their colors, the chemical composition, of course, distances that they are away from us, and so on and so on. Different types in terms of their spectroscopic properties, and so on. Here also, I showed only one example, the diversity in terms of size. And you can see this is the real comparison, and you can see that actually galaxies can have very, very different sizes, and sometimes even some of the structures, components that galaxies have, like in case of this galaxy here, or this one here on the bottom, where we have these very these relativistic jets of the material ejected from the central part of the galaxy. You can see that even the distances that this material can reach inside the intergalactic medium can be even several times larger than the size of the galaxy itself. So these galaxies here, actually, where you can see these big jets, are some of the examples of the active galaxies that we will speak about in this talk. Here I put one of the links to the video where you can see the 3D presentation about also different sizes of galaxies. And it's nice to use it for the outreach. Let me check if I can go to the slide. Properties that we are observing in galaxies, also galaxies can be in very different environments. So this is just one of the examples. So it means that the galaxies normally are not isolated in the universe, but they do attract between themselves with their own gravity, and then they form bigger systems that we call either groups or clusters or superclusters and so on. So here you can see some of the galaxy clusters. And then also we have all different types of for example, galaxies also interact and they even merge. And here you can see just different types of galaxy interactions and mergers. So we have people in astronomy that are really studying all these types of interaction, mergers, how interaction and mergers of galaxies contribute to the galaxy evolution. And nowadays, actually, we know that the types of galaxies that I mentioned previously, where we have irregular, in terms of the morphology, irregular galaxies, spiral, lenticular, and then elliptical galaxies. These galaxies, beside the difference in their morphology, have also very different properties. So we know that spiral galaxies are in principle much younger galaxies than elliptical galaxies, and we know that the most massive elliptical galaxies are actually forming through the merging of two spiral galaxies. So once again, the interactions and mergers of galaxies are really important for understanding how the universe was evolving across the cosmic time. Then galaxies in terms of their star formation. So how many stars galaxies actually form in one year. So for example, for normal galaxies, we will have about one star formed per year, but then we observe in the universe amazing events such as starburst galaxies, like some of the examples that you can see here on this slide, where we have several tens or even hundreds of stars being formed per year. So we have a very, very strong star formation going on in these galaxies. And one of the principal reasons is actually the one that before coming to the starburst phase, these galaxies went through certain interactions galaxies, and this is what will be the main part of our talk here. So these active galaxies, some of the examples you can see on this slide, and you can see that some of them have, once again, these relativistic jets, but not all of them. So the other two are also active galaxies, but we don't see these jets, also because we have the optical images. So basically, when optical data and when we observe, we don't really see active galaxies just visually, no, in terms of their morphology, for example, no. So here you can have we have the subsample where you can see that just visually we are not really able to say which galaxy is active or non-active. If we go to radio, that can be different in case that those galaxies have these relativistic jets that we really observe only in case of active galaxies and not normal galaxies. So these they are so special and so interesting what we call AGN, or active galactic nuclei, in their center. So, and these galaxies are some of the most luminous sources that we have in the universe. So when I say some of the most luminous sources, it means that their luminosity can be hundreds or thousands or even tens of thousands of times or even more than that higher than what is the luminosity of normal galaxies. And the question is really why, and people really during a long time in the past century were trying to deal and to understand the principal mechanism that is responsible for these high luminosities. Being so luminous sources, these active galaxies are extremely important to be studied in astronomy, because you know that as we are observing sources that are further away from us, that are more far away, we are having observational difficulties to really detect them. So if the galaxies are bright, it means that we have more opportunities to observe them with our telescopes. And I think you also know that as we are going further away in the universe, so those galaxies that are more distant, that are further away, are also younger. So when we observe galaxies that are further, we observe galaxies that live in the universe that is younger, which means that if we have the opportunity to observe active galaxies, these are the sources that can really tell us more about how the universe was at different cosmic times. And basically, when we observe the most distant galaxies, all most distant galaxies and some of the youngest galaxies that have been observed in the universe, in the early stage of the universe, are actually active galaxies, galaxies that have the AGN in their center. Now again were discovered at the beginning of 20th century, when people using spectroscopic data and observing emission lines, absorption lines that we can see in spectra, they observed very strange emission lines. And then they also, using radio observations, observed for the very first time in some of the sources, nearby sources, those radio jets that I mentioned previously and that you've seen in the image when we compared the sizes. So at the beginning, people really didn't understand what is going on, because before observing these galaxies, astronomers were studying spectra. So basically the light that we are receiving from galaxies and from the stars is the basic information for us in astronomy. And when we take that light and we disperse the light using some of dispersive elements, such as the prism, or nowadays we use the spectrograph that again has different types of dispersive elements inside, then we can obtain spectra, which means that basically the light that is coming from celestial sources, we can observe we can decompose, we can observe different components of that light, and then observe different features in our spectra. So basically, previously, before these active galaxies were discovered, astronomers were used to the spectra that was coming from the stellar sources. So even they observed galaxies that are normal, the total light of the normal galaxy would be the light of all the stellar component that that galaxy has. So basically, if you take spectra of each individual star and then you put all tens or hundreds of billions of spectra together, you will get the spectrum of one galaxy. But when the first active galaxies were observed, astronomers started observing very strange features. So basically, the emission lines coming from different chemical elements and being much broader than what it was observed previously. So the big enigma and of normal and active galaxies are not the same. So this is what I mean a little bit. Here I put the example where you can see how the spectra of normal galaxy looks like on the left. And then on the right, we have two examples of two types of active galaxies. So you can see when I say emission lines, you can see all these features here that are very, very broad. So basically, I don't know if you can see my cursor, but here when we go to the normal galaxy spectra, and after 6,000 angstrom that we have here, you can see here also emission line features. So these emission line features are exactly the same ones corresponding to H alpha, so the hydrogen line and two nitrogen lines, the same as you can see here in this spectrum on the left. But as you can see on the left, we have much stronger lines and much broader lines. So this was one of the main points for detection for the first discovery of active galaxies in optical. And then when the radio data came and when the relativistic jets were discovered as well, that was another, in these active galaxies, that was another important difference from the normal galaxies. So here now I will just some of the differences between. So the first is interluminosity. So for the normal galaxies, we have normally below 10 to the 11 solar luminosities, that is the luminosity in optical range. However, for active galaxies, we can have, as I said, even up to 10,000 times larger luminosities than in the case of normal or inactive galaxies. So these are big differences. The thing is the galaxies, the very central part, the light coming from the nuclei, from the very central part of the galaxy, is much lower. So we have lower luminosity, significantly lower than in the case of active galaxies. So just to give you an example, for active galaxies, the light coming from that nuclear region can be, as we said, about 10,000 times higher than what is the light coming basically from our entire Milky Way. However, if we go to the sizes, the size of the nuclear region from where we are receiving these 10,000 times higher luminosities than what would be the total luminosity of normal galaxy, the size is about, as you can see here, 0.0032% of the Milky Way size. So we are really speaking about very particular process, a very particular mechanism for generating these huge luminosities and great emissions of energy. So here on the top, in the right, is one comparison with something that is more easy for us to understand in terms of the comparison of the sizes. So, and that I like to compare with. So if we consider that the Milky Way size is, let's say, the size of the United States, or let's say the size of this big green circle that you have, and we said that AGN has, and then that the AGN that is in the center of this green circle gives 10,000 times larger luminosities than the light coming from all the stars that are in the Milky Way fulfilling this big green circle. However, if we compare now the size of the AGN giving such big luminosities with the size of this big circle, then the size of the AGN would be even smaller, or let's say comparable with the grain of the dust. So if you compare the grain of the sand, the dust or the sand, with the size of basically United States, that's similar with what we are talking about, the size of the AGN and the size of the Milky Way, where we are, however, having much larger luminosities coming from the nuclei. So once again, this means that we are really speaking about very powerful and very particular mechanisms. Another difference between normal galaxies and ability in luminosity. The light, the brightness, luminosity, or the brightness of the galaxies, these active galaxies, is changing across the time, while for the normal galaxies, we normally have, do not observe the change in the luminosity. So basically, very often the variability in active galaxies can be very strong. So it can even, the luminosity can even change in terms of minutes or hours. And basically, for the luminosity here, I put the example that in order to have the change in luminosity in 1 hour, it means that the source needs to have a size that is less than the speed of light times 1 hour, which is about 7 astronomical units. So 7 times the size between us on the Earth and our sun. So that brings us to the point that we can actually measure the size of the AGN, and we can see that AGN are really very compact sources. And then another in normal or inactive galaxies, we don't observe in radio these or in X-rays the signs of these relativistic jets that you can see here. However, in a certain number, not in all of them, but in certain number of active galaxies, in about 10% in the very local nearby universe at higher redshifts, we still don't have the good statistics. Hopefully we will be able to deal with it in future with future missions. So this is again one of important. And another difference is also in terms of the normal we receive from normal galaxies is emitted in optical or the visible part of the range in electromagnetic spectrum. However, when we speak about active galaxies, they are really strong emitters in X-rays and gamma rays as well, in infrared, and then in radio waves as well. So when we discovered active galaxies, I have to say that this opened huge possibilities for research, and actually it brought to an amazing development of different parts of physics, such as high energy physics in gamma rays, X-rays, and then low energy physics in radio and in infrared that previously was not really developed in such a way. So really, in order to understand the properties of these galaxies, we pushed the development of technology in other parts of physics. So they are really studying these sources. We really managed to extend our knowledge in physics in different parts of and here you can see one Centaurus A, and on the right you can see 3 images. One is X-ray, another is radio in the middle, and then optical image. And you can see that these 3 images really look very different from each other. And basically, it's the same galaxy. If you would see these 3 images separately, none of us would say that this is the same source. However, it really is. And finally, the real image of Centaurus A galaxy is the one that is in the center, which is a composition of these three images on the right. So basically, you can see here that the multi-wavelength study, which means if we observe now this active galaxy from gamma rays, X-rays, all up to the radio going through the optical, we are actually getting information from different physical processes that are going on inside the galaxy, from different types of sources, stellar sources that we have within this galaxy, and then putting all the information together is the only way that we can study the complete physics behind. Basically, multi-wavelength observatory not only in X-rays, in ultraviolet, infrared, microwaves, and then radio, really brought again a revolution in our knowledge. And basically, without multi-wavelength approach, we cannot really understand fully the physics that we have behind different celestial sources, and we can really not understand fully the universe in general. Hopefully, I hope I managed to show you how really strong emitters these sources are. And now we want to see how do they generate the studies. People saw that actually the main mechanism of producing these strong energies in active galaxies is the accretion of the material onto the supermassive black hole that all of these sources have in the center. And these supermassive black holes can be thousands of millions or hundreds of millions more massive than what is the mass of our sun. And due to the accretion of the material onto this supermassive black hole, we have huge liberation of gravitational energies, and this is the principal mechanism responsible for the huge emissions that we are then detecting at different parts of the electromagnetic spectrum. Exist. Actually, we now even have the observational evidence, as you know, through the Event Horizon Telescope project, that supermassive black holes exist. And here are some of the evidences, observational evidences. So using spectroscopic information and measuring the profiles and widths of these emission lines that I mentioned previously, and comparing with the stellar components, we can see that we have the supermassive black holes in the centers. The variable emission variability that I mentioned also previously is another evidence, having the fact that we have the compact sources in the center, and strong variable sources is again giving us the fact that the supermassive black hole is there, as I said, as a very compact source. Then having the radio jets that are collimated and straight is giving us signs that we have actually single rotating body and not a source made of several components, several bodies. And then finally, we can also measure the velocity dispersions. And by measuring the velocity dispersions, we can measure the mass that we have in the center of the galaxies. And therefore, we see that we are dealing with really massive and non-stellar sources. And as I said, these are some of the principal evidences that we have for having the supermassive black holes in the centers of these galaxies. Nowadays, we know that almost all galaxies, basically all galaxies, do have supermassive black holes in their center. But it doesn't mean that all of these galaxies are active. So for having the activity, you do need to have the liberation of these huge emissions, energies that we mentioned. And to have that, you do need, beside the fact to have the supermassive black hole, you also need to have the accretion of the material onto that black hole. So you need to have the material plus the mechanism to bring that material onto the central part, onto the black hole, to be accreted in order to have the nuclear activity. This just I will not go through all these types of the AGN. I just wanted to show here that basically we have the so many different types. So it's basically a chaos. We have different classifications using radio data, optical data, and then observing spectroscopic properties and so on and so on. Even using X-ray data, we have different classifications. So it's really a chaos. And then we do also have what we call the standard model of the AGN. And in this standard model, we have different components. So the first one is the supermassive black hole in the center that I already mentioned, and then the accretion disk. We also know nowadays that we have, after around that, we have the torus of accreting material that will be accreted onto the accretion disk, and then the supermassive black hole. And this torus, along the history, was studied really a lot, and different models are present in terms of the properties of the torus. Then we can have or not the radio jet, relativistic jet of material that I mentioned already. And then we have different areas that we call broad line region, narrow line region, with the gas that is much hotter and closer to the black hole, that from where we are getting those broad emission lines in our spectra. And then the part of the gas material that is a bit with lower temperatures, giving more narrow emission lines that we observe in our spectra. So in this standard model of AGN, it was also suggested that then, depending on the presence or absence of the relativistic jet, and then the orientation, how the AGN is oriented toward us, we can actually see different types of AGN. And that is what we call the unification model. And this unification model has been also studied a lot, and we also nowadays know that there are many, let's say, parts of the unification model that are not really, that are having problems to explain different types of AGN. So we are still really in the process of understanding why do we have so many different types of AGN. And we also know nowadays that AGN can change from one type to another. So it's really very, very complex world, very diverse world. This is just a very brief summary. I think I should a bit speed up in order to come to the second part. So this is a bit why shall we care about AGN? So why they are really important for us. So the first is the very peculiar, very complex physics that we have. When we come to the AGN properties, we are dealing with a physics that is not classical anymore, that is not Newtonian. We are dealing with physics where we are entering into the relativistic conditions, in terms of the properties of the matter, in terms of the velocities. So that really brings us, it opens a field where we have big challenges, and it really can bring us to new scientific, to new knowledge generation, and also to technological developments and innovation. We are dealing, as you were able to see, with high energetic sources. So as I mentioned previously, studying AGN really contributed to big development in X-ray, gamma-ray physics, and then instrumentation, that nowadays we use X-ray instruments in medicine for different diagnostics, in agriculture for different applications, and so on. It also has, we also have the possibilities that these sources can be related with the origin of the cosmic rays. Cosmic rays are everywhere, are present everywhere in the universe. They're again high energetic particles, and they're very, very important for the space weather. So basically, all the satellites that we have orbiting our Earth, that nowadays we have thousands of them, that are costly and then very important for different applications in our society, they can be damaged by cosmic rays. And in order to really know how to protect our technologies, our instruments, and to improve our technologies, we really have to understand what the cosmic rays are. And we are still on the way in understanding that. Then active galaxies, as I said, are really very important for understanding galaxy formation and evolution. Once again, being the most luminous, they're important cosmological labs. By observing these galaxies, we can, it's the only way for now to observe how the universe was when it was young. So by studying these galaxies at different cosmic times, we can see how actually they evolve in different so now the second part, go through the summary of the research that we are doing under the ESSTI regarding AGN. And you will see that there are actually many projects going on. The institute was established 4 years ago, and I think you all know the motto that the institute has, that we explore the universe for the benefit of our people. And astronomy astrophysics department is one of many departments that we have at the institute. And under this department, we have 3 basically well-established research groups in stellar astronomy, in extragalactic astronomy, and then in cultural astronomy. So I'm the one who is running the group in extragalactic astronomy. Most of the study that we are doing in current research focused on understanding the physics behind these active galaxies and also contributing to the fundamental knowledge building and then to the further hopefully projects. So these are the main aims regarding science. When we come to the development, that we can see that also either doing study and research in AGN that are so far away from us, we can still contribute in a significant way to development of our society. So first, we can contribute to the development of astronomy and science in Ethiopia and Africa. We can contribute to give more visibility to the institute that is still very young and to the astronomy astrophysics department, and open the doors for future projects, not necessarily in the field of extragalactic astronomy. We contribute to strengthen international collaborations, which again opens many, many possibilities, and you will see that now through different projects. We definitely contribute to the human capacity building, and hopefully more in future than what is currently to Entoto development as well, and then to the educational development in Ethiopia and then in Africa as well. When we research in active galaxies or AGN, here I listed all of the things that are related with our work. So we use physics, we use maths, we use high energy physics, we use multi-wavelength observations from X-rays up to radio and gamma rays. We use multi-wavelength data reductions where you have to learn about different softwares. That definitely contributes to different improvements in terms of technology, and we need really strong people develop strong computing and programming skills. We are dealing with huge data sets. So you learn by doing your master or PhD in extragalactic astronomy. You get familiar with big data, how to manipulate with big data, how to analyze the big data, the use of softwares that after you can apply to many different fields. Statistical methods that again you can apply to other fields. Machine learning that we are every time more and more used to, numerical modelings, and then finally also you can use the work that we are doing for even outreach education, like the current situation when I'm giving this talk we are running. And I will not go into the details, and hopefully into the details for not let's say bringing too much information, but feel free after to ask more if you would like to obtain more details. So one of the projects that is basically focused on my own research that I'm trying to do in the free time that I have, and I don't really have much. It's related with studying the stellar populations in those active galaxies that have very, very strong emission in X-rays, so that are extremely high energetic sources. Some of the most high energetic sources that we observed in the universe. So I want to understand what kind of stars, or let's say stellar populations, these sources have. For that, we are using, this is a project that is done in collaboration with my colleagues from Spain. And for that, we are using the public data with a very recent survey of these galaxies. And it's the very first time with this project that we are trying to study the stellar populations of this particular sample. And with Teleke, in collaboration with Spain, and then GLACE survey, that is international survey, we are trying to understand the properties of galaxies in galaxy clusters. So basically, you remember at the beginning, I mentioned that galaxies can have different environments. So those galaxies, when they are making a system of basically hundreds of thousands of galaxies, we call galaxy clusters. And in Teleke's research work, in his PhD, what together we are trying to do is to understand the morphological, how the morphological properties, nuclear activity in galaxies, and other properties such as chemical composition and stellar properties change along the cosmic time. So we published already one paper last year, one preceding paper, and the second paper of Teleke was also submitted recently. And the monthly notices that you will see here is really it's the most prestigious journal in Europe in regarding research publications in astronomy and astrophysics. So we managed with work of Teleke to, for one of the clusters, to really get the most detailed catalog with morphological properties of galaxies. In the second paper, to bring the biggest sample of emission line galaxies in the cluster. And we went through the comparison of 3 different clusters along the cosmic time. Study, and now he's currently doing his PhD in South Africa. So with Antoine, what we are studying is we are comparing the properties of active galaxies and non-active galaxies in what I put here, the green valley. And this green valley is the area, it's the transition area where the galaxies, in order to go from spiral, or let's say younger galaxies to older galaxies or elliptical, they do pass in terms of their color properties through this, what we call green valley area. So in that green valley area, we want to study how the active galaxies compare with non-active galaxies, and then understand what is the role that nuclear activity in galaxies can have on this morphological transformation of galaxies and galaxy evolution. So with Antoine, we really managed to get very interesting results for the very first time by doing the study in the far infrared. We published one paper from his master's study. We published the second paper at the beginning of his PhD. And now we are with another 2 papers. The third one will be submitted hopefully by the end of this year. And as I said, we really managed to get very, very interesting results. Morphology of active galaxies, and it forms the PhD thesis of Tilahun. So with Tilahun, we are dealing with big number of active galaxies, and we want to understand what kind of galaxies they are in terms of morphology, in terms of their shape. But when we have galaxies that are very far away, this nuclear activity, the AGN that we have in the center, can contaminate our morphological classification. So with Tilahun, for the very first time, we are obtaining the most detailed study on how the presence of AGN can affect the morphological classification of galaxy. And then with the results that we obtain, we will reclassify the galaxies that have been previously classified in one of the surveys without taking this AGN contribution into account. So currently we are also working on 2 publications during his master, the study in AGN. He did a master in at ESSTI. Now he's currently in Chile doing his PhD. And with Dejene, we recently published one paper with all the results. And in this study, we used the previous results where people saw that there is a specific mass of galaxies that for that particular mass, it looks that the galaxies have much larger rates of their growth. So converting gas into the stars, basically. So we wanted to understand in more details what kind of galaxies these galaxies are. And we obtained very interesting results where we saw that these galaxies are actually very good candidates of being in this morphological transition from young galaxies, moving from young galaxies into in collaboration with Rwanda, Uganda, South Africa as well. So it's a very nice African collaboration. And with Beatrice, we are also studying those galaxies that are in the Green Valley that I mentioned previously, but we are studying different selection criteria. We also got interesting results here where we've seen that different criteria that have been used previously in different literature, where at the end people are bringing different conclusions, are actually really affecting the sample selection. So depending on one criteria or another that is used, we are selecting different types of galaxies. And we are now preparing the paper that hopefully will be submitted soon. So this work was done during the master study of Beatrice, and now Beatrice is starting. The project is focused to luminous active galaxies that we have in the universe. And it forms part of Schimelle's thesis, and it's done in collaboration with Spain and Italy. And here we are trying to understand actually the connection, the dichotomy between those quasars that do have these radio jets that we mentioned previously, and those that don't, and how these jets affect the properties of the gas around the galaxy. Who also did his master at the ESSTI and got the scholarship also for his PhD in Chile. And with Astrate, we are studying the new photometric estimation or indicator of the accretion rates. So how strong is the accretion? Could be the accretion in active galaxy. During the paper, we studied different morphologies for the very first time of the most luminous sources in X-rays, but trying to see how their morphologies are changing when we go from X-rays through optical and then to radio. Astronomy student, the first master astronomy student in Tanzania, and with Daudi during his again master project, we studied the properties of those active galaxies that have very low luminosities, trying to understand how we can really efficiently separate them from other galaxies that have similar luminosities but don't have the AGN in their center. I'm doing her master, and with Jeru we are dealing with the variability. You remember I mentioned previously that active galaxies can be very variable. So we selected a sample of quasars, very luminous active galaxies, and we are studying their variability. So we have from the public sources, public data, how the variability, how strong variability parameters are, and we are seeing how these parameters are changing, and if they are changing with different properties of quasars. And this is a bit so I think through all these projects, we definitely can contribute to the science development, astronomy development, and knowledge generation, but also to the human capacity building. All people that I mentioned that are doing their master PhD are already connected with some of Ethiopian or East African public universities. So once they finish their studies, they will go back to their universities and then continue teaching. And in that way, we can really improve even the level of education in Ethiopia. We can contribute to technological developments. We definitely give more visibility to the ESSTI and the science that we are doing in Ethiopia. You've seen that most of the projects are actually having international are based on international collaborations with Spain, with Chile, with Italy, with South Africa, Uganda, Rwanda, and so on. And also we managed really to contribute to the institutional development of the summit we organized last year. It's the very first International Astronomical Union Symposium that was organized in Ethiopia. It was the third one in Africa to be organized in the last 100 years. And the topic was the nuclear activity in galaxies across cosmic time. So we used this to really bring many of the international colleagues for the very first time to Ethiopia from more than 30 countries. And we also use that to benefit the broader community, and in help of the Ethiopian Space Science Society, we managed to organize different outreach activities in different schools, public talks, teachers trainings, and also the students training. So thank you very much for your attention, and I'm ready for questions.
Okay, so thank you very much, Mirjana. That was very good, very deep insight into active galaxies and the active galactic nuclei. So thanks again. So when we proceed to questions, I've only had 2 so far. I think everyone, you can use the question box or the chat box to forward your questions you have. The first question says, why could the concentration of matter at the center of an active galaxy like M87 not be made of stars? So, Mirjana.
So why, can you repeat again?
Why could the concentration of matter at the center of an active galaxy like M87 not be made of stars?
Okay. So I will a bit correct the. Well, I will give the answer that hopefully will also change a bit the aspect of the question. No, so basically we do have. It's not that we don't have stars in the central part of the galaxy. So we basically have stars so the galaxy itself is a system of stars, and then within in the space between the stars we have the different amounts of gas and dust that is fulfilling the space. So that is a bit the concentration of stars, and then the concentration of what we call the interstellar medium is changing along the galaxy as we are going from the central part over the outskirts of the galaxy. And then also the concentration is changing in terms of other parameters, such as morphology and so on, you know. So in the central parts of the galaxies, we also have stars, and actually we have much larger concentration of stars than when we go to the outskirts. The biggest concentrations of stars are actually in the central part, in the inner parts of the galaxies, and that's where we have the part of the galaxy that we call bulge, that beside being the most concentrated with the stars, it's also the oldest part of the galaxy. And then less concentration we have in the rest of the galaxy, or let's say in the disk, more disk part of the galaxy, in case of the spiral galaxies, and for the elliptical in the outskirts. So again, in the inner parts and the central parts of the galaxy, we also have stars. When we speak about AGN, so for the AGN, in what is the nuclei, what we call the nuclei, or the very central part of the galaxies, instead of having individual stars, what we observe is that we have these supermassive black holes. And basically, these supermassive black holes are results of the formation of the galaxies and the evolution of the galaxies along the whole cosmic time. So basically, since the galaxies were formed up to now. So during the whole life of the galaxy, the stars were basically merging, making in the center of the galaxy every time more and more bigger. So not only the stars and all the material was accreting constantly across the lifetime of the galaxy into the central part, making and bringing this supermassive black hole to be more and more massive. So I don't know if that is clear, and if that answered on the question, if I understood the question well, or if there are other questions in relation with this.
All right. I think if it's unclear, you can go ahead and write again in the chat box or the question box. I'll proceed to the next question. It says, can you revise again? For this one, I think you should Adonai Mulgeta. I think you should make it clear where you want the play to be revised again. The next question says, is there a magnificent danger resulted by active galaxies?
A danger? I don't know what do you mean? I mean a danger in terms of the life for us, like our planet and the life on Earth.
Yeah, I think so. I think so, probably, or maybe in the future, something that could happen.
Okay, so in universe we are talking about such great scales in terms of the distance, and then also in terms of the time. So the sources that we are observing, even being so luminous, are not really don't have basically any significant influence on us. So active galaxies were existing in the universe since basically the universe since the very early age of the universe up to nowadays, and they've been emitting the light, and as I said, I mean, that light is not affecting us in any significant way. One of the possibilities that I mentioned previously, that we are constantly having in the universe and receiving here on the Earth as well, the cosmic rays, so the high energetic particles. These particles, when they are, even if, I mean, the AGN could be one of the sources of their origin, during the path that they have to go through from their origin until reaching us, they lose a lot of their energy. So basically the answer is no. If the question is related with danger per life on the Earth and our planet, we don't expect any danger in that aspect.
So the next question is from Seaside, and it says, what would it take to make the Milky Way galaxy active? And if it had become an active one, could there be a notable change in our night sky?
Okay, so basically for the Milky Way galaxy, it's a nice question from Seaside. So for the Milky Way galaxy, very often we get a question if the Milky Way galaxy is active galaxy, no? So you remember that I said at some point that basically nowadays we know that basically all galaxies do have the supermassive black hole in their center, but it doesn't mean that even so they are active. So beside the existence of the supermassive black hole, we do need to have the efficient mechanism that will bring the material to the central part and then accrete that material to the supermassive black hole. So nowadays we do know, we have observational evidences that there is a supermassive black hole in the center of the Milky Way. It's Sagittarius, we call it Sagittarius A. And we also know nowadays what is the mass of the supermassive of that supermassive black hole in the center of the Milky Way. We don't know. There are possibilities that Milky Way in the past was active galaxy, because we know that galaxies, that's something that is important to stay with. Galaxies are constantly changing, like everything else in the universe, are constantly changing with time. So when we speak about active galaxies, it doesn't mean that galaxies are born as active with AGN in their center and then they die as active. Galaxies being active is only a certain phase during their lifetime. So the galaxy can be normal or inactive and then suddenly enter in the active phase and then stop with the nuclear activity and become normal again, and so on. So for the Milky Way in particular, it was maybe more active in the past when it was younger and when we had more material in the galaxy accreting onto the central part. But nowadays, even we have the supermassive black hole, Milky Way doesn't show the nuclear activity. But we know that Milky Way and Andromeda Galaxy, that is one of the, it's the nearest galaxy to the Milky Way, and that it's not the out of the dwarf galaxies or satellite galaxies. We know that Milky Way and Andromeda Galaxy are approaching themselves. So they are moving toward each other, being attracted by their own gravity. And we know that if we continue, if something strange doesn't happen in the universe, we expect that these two galaxies will merge. And we expect that this merging will happen in a few billion years from now, in about 4 billion years. And when these two galaxies merge, then we do expect that for the final result that we will have, we can have the source that again enters in the active phase. So basically, with the galaxy merger and interaction between Milky Way and Andromeda Galaxy, the final result will be the basically creation of one massive elliptical galaxy, but that galaxy will go through different phases. So once the two galaxies merge, we will go to the phase of the strong starburst activity. So a lot of stars that are created, and also through the AGN activity as well. However, again, regarding the life on the Earth, and then in the solar system as well, in that aspect, of course, we do speak about very, very significant changes. The time that we are predicting for this merging is also corresponding to the time where the sun will progress in its evolution and basically enter in the phase of the red giant. And when the sun enters in the phase of red giant, where the size of the sun will increase significantly and basically be come even out of what is currently the orbit of our Earth. So we basically expect that Earth will totally evaporate. So before that, we even expect that the oceans will disappear. So we basically expect that the life on the Earth will disappear even prior to that. So definitely, I mean, that will make significant changes within the whole Milky Way.
Okay, thank you for the very, very nice explanation. So I think we're lagging behind time a little bit, so I'll try to go through the rest of the questions a little bit more faster. It says, what are the forces that heat up the acceleration disk? This is a question from Robel Brook.
Okay, so I suppose the question is focused on the accretion disk,
Yes.
not acceleration, but yes.
Sorry.
For the accretion, yes. So for the accretion disk, actually, the forces, I mean, the mechanisms that bring, the question is very good, because definitely without, as we said, without accretion of the material, we will not have the nuclear activity in galaxies. But what are the mechanisms responsible for bringing the material onto the supermassive black hole is still one of the open questions. So we are still in the way of really understanding the process, the main mechanisms that are bringing the material onto the central part. So basically, you need two things. On one side, you need first enough material. First, you need to have the material, substantial material, to be brought to the central part. And then you need also the mechanism or the force that will bring that material to the accretion disk. So some of the, as I said, it is a still open question. So we still don't understand the whole picture fully. And we suppose that that picture also doesn't have only one answer, because we observe different types of AGN. So we can have different also processes or mechanisms, but definitely some of the suggestions are that interactions, galaxy interactions or mergers are one of mechanisms that could do the two things. On one side, to bring them to have the to be responsible for origin of the material, and then also to bring the material to the central part. Then also another mechanism that was suggested is the presence of the bar. So basically, the nuclear, in the spiral galaxies, we observe, not in all of them, but there is a part of spiral galaxies that have a certain nuclear bar, and it's been suggested, it's been observed that many of these barred galaxies are also active. So this could be also one of the mechanisms of bringing the material onto the central part of the galaxy. So these are some of the two possibilities, but they are not the only ones.
Okay, awesome. So next question is from David Brahanu. So it says, why quasars? Why were quasars generally so much more luminous why do they put so much more energy than active galaxies?
Okay, so basically, for quasars, we have, it's a bit, it could be, but it's still one of the, again, issues that we have really to understand very well. But basically, using the standard model of AGN and the unification that I spoke about previously, we believe that when we are dealing with quasars, we are actually looking straight to the AGN. So in these sources, instead of having the view that is, instead of receiving the information that is coming from, let's say, the material that is surrounding the supermassive black hole that is obscuring torus, we are really having the sight straight to the AGN. So we are observing directly the supermassive black hole, the accretion disk, and then all the emission coming from the narrow line, broad line region as well. So having the straight vision to the AGN is then giving us also the we are receiving much larger luminosities of these sources.
Okay, great. So the last question from the chat box that I'm seeing is, what determine the activity level of an active galaxy? It's from Adonai Mulugeta.
I also got, again, the connection was a bit interrupted. What determined
the activity level of an active galaxy? Like,
okay, so yes, so basically, in order to say how active the galaxy is, we normally refer to the luminosities. So we will, that's one of the, I mean, there are actually different possibilities that we can, I mean, different parameters that we use to say which galaxy is more or less active, but luminosity is one of the principal ones, the principal properties. So when I say luminosity, we compare the luminosities in different parts of spectrum. So in terms of optical luminosity, in terms of X-ray luminosity, in terms of radio fluxes or luminosities. So in all these cases, although going to the high energies or to the lower energies, we can say if the galaxy is more active or not. So basically, for those galaxies that have higher luminosities, either in optical or X-rays and so on, we say that they are more active. That would be the simplified answer.
okay, awesome. So I have other couple of questions from my side, but I think Kira has one, so I'll pass it on to him. Kirubel?
Yes, can you hear me?
Yes, I can.
All right. So I have some questions, but I think you have answered most of them. I have 3 on my hand right now. The first would be, can we use AGN to measure, to do measurements like standard candles, the way we use them, or the way we use supernova to measure lengths in the universe? Can we use AGN, and how consistent are they to do such measurements?
Mm-hmm. Okay, shall I reply, or you want to say another 2?
Yeah, I think one by one would be perfect, right?
Okay, perfect. Yes. So when we come, it's a good question. So when we come to the AGN, using AGN as a standard candles, it's a bit difficult because of what I said, because of such a big diversity that we are observing, and also because of in their properties, and then in particular in terms of variability. As I said, many or most, or maybe even all of active galaxies are actually variable sources. So we still don't have, because to study variability, you need a lot of observational time. So we still are actually, in comparison with many other studies of active galaxies, when we come to the variability studies, we are still very poor in our knowledge. So we hope that with new observations, especially when LSST starts, we will be able to study variability in galaxies, in active galaxies, much better. But since these sources are variable, then it means that their luminosity is changing with time, and then that makes difficult their use as standard candles. However, for quasars, there are some studies. Actually, one of our colleagues that is involved in Shimele's thesis and the study of quasars that we are doing is one of the pioneers in that aspect. And Paola is the one suggesting that quasars could be used as in cosmology, even as a standard candles. But still, it's one of the open issues. So still, I think we need much more observational facts, especially when we go to larger distances, higher redshifts, in order to really provide the answer on that question. So for now, we don't really use AGN as standard candles.
All right, that was amazing. So the next one would be, what role do they play in material formation? I mean, for most of the materials other than hydrogen, helium, and lithium, most of them are formed in stars. But since active, the AGN is so hot, and high mass elements can be formed in the galactic center. So how much materials can they be formed?
Okay, so it's perfectly true. So these galaxies are, I mean, the active galaxies and AGN activity is really contributing to the change of the chemical properties that we are observing in galaxies. So in case of the spectra of these galaxies, as I said, the principal difference with normal galaxy is really the presence of very strong emission lines. And very strong emission lines that are coming from the chemical features that we don't really obtain in an easy way in stellar spectra. So we speak about high ionization lines, such as the different oxygen, such as oxygen lines with different levels of ionization, the nitrogen lines, helium lines, iron lines. So iron lines are there as well in emission in active galaxies, and that's one of principal evidences that we are really having the AGN in the galaxy. Then when you go to the higher redshift sources and quasars, we see the very strong emission even in carbon lines, in magnesium lines, and so on. So we really have the opportunity with these sources to study the astrochemistry in many details, no, and to really learn a lot about the chemical elements that we have in the universe and their properties.
Great. So my last question would be, what is in the horizon for the future of AGN research, mysteries to solve and all? Thank you very much on the way out.
Okay, thank you, Kirubel. So for the future, we actually have so many open questions still to answer. So one of the hot topics now is exactly what we call the changing look AGN, which means that we see these active galaxies going from one type to another type. Then, as I said, we want to really still understand how the active galaxy is becoming actually active. What is the role? We still don't understand fully what is the role of AGN in the evolution, in the evolution of the galaxies, and then in these morphological transformation from spiral galaxies into elliptical galaxies, or let's say from younger to older galaxies. The variability, as I said, is one of the issues. Also, how the AGN affect the rest of the galaxy properties. So let's say the AGN, what we call the AGN feedback, but also how the other galaxy properties will affect the properties of the AGN is another question. Then when we go to different parts of electromagnetic spectrum, we again still have a lot of open questions, such as the relativistic jets. We still don't really understand how these relativistic jets that we mentioned really form, and how do they evolve across the time, if the galaxies, what is really the, again, the triggering mechanism for having these jets, how again these jets affect the surrounding material in the galaxy, and so on. And then in general, what is the role in galaxy formation and evolution across the cosmic time and across the evolution of the universe is one of the major questions, I would say. So basically, we cannot really understand the evolution of the universe without really fully understanding the nuclear activity in galaxies.
All right, that will be all. Tensei, over to you.
Thank you, Kirubel.
Thank you again.
Okay, so my question is not much of a technical thing. So first off would be, I was pretty amazed and fascinated to see a lot of young Ethiopians, you know, taking like research and seeing all those projects on your slides. And I was thinking like, so this is a very interesting topic, and what's actually hindering like our scientists and like our fellow scholars to do groundbreaking research, and what could Ethiopia do in that regard?
What Ethiopia can do?
Yeah, in that regard, so that like more, I saw not just Ethiopians, like a lot of fellow students from lots of other African countries are coming doing research, joint projects, and doing a lot of good things. And what could Ethiopia do so that they could do even more groundbreaking research?
Yes, so I think in that aspect, it's a bit not only for, I mean, I would say it's the same what we can do not only for AGN study, but for the research in astronomy in general. No, so on one side, making it really possible for our young people. I think one that they remain in research. No, so you've seen that, as you said, we currently have. People that are involved, that are doing their master, their PhD. Some of them even did their master in Ethiopia. Now they are doing that, or in Rwanda, Uganda. Now they are doing their PhD abroad. We hope that even those that are doing their PhD abroad, when they finish, they will come back to Ethiopia. But I have to say that one of the difficulties, principal difficulties that I observed when people finish their PhD or their master, and then the fundamental thing is really that they can remain in science, which means that they need to have efficient time to dedicate to their research. And one of the principal things is that when they go back to the university, which is great because, as I said previously, in this way, we really contribute to improving the level of education in Ethiopia and across Ethiopia, not only in Addis, which is very important. For me, one of really important things is that the students, I mean, people that I'm working with, they are really having their lecturing positions, university positions all across Africa. Seleki is near Addis, Tilakon is in Bulehora, Shimeles is at Jima University, and so on and so on, you know? So that means that we can really contribute to improve the level of education across Ethiopia. But if people that finish their PhD and really finish with great results, because I can see the progress in all of the people that I started working with, an amazing progress as the time is passing. But if they go back to their university and they are so much into teaching and lecturing, having so many undergrad students, and they don't have sufficient time to continue with research, it will be very difficult that they can, at the end, even supervise efficiently their students, future students. So I think one of the first things that as a country we should try to do is to really put jointly efforts. I don't know how, because it's not easy. I mean, these things are happening because basically we still don't have enough qualified people even at the university, and many of the lecturers are also going through their master PhD studies and so on. But it's at least something to have in mind, you know, that if we want to remain with the science and research, it's not only enough that people do their PhD and get the great results during their PhD. They really have to remain in science. For me, for example, after my PhD, I was not feeling myself sufficiently strong to, for example, supervise PhD students. I needed at least several years to work myself on my research, to go to extend my knowledge, extend collaborations, meet more people, enter into different fields in order to really start supervising master PhD students after getting experience. And the difficulty that we are getting in Ethiopia is that people go back to university and directly they have the obligation to supervise other students. And then that really can bring a lot of frustration as well. So that's one thing. And then I think in terms of the funding is another thing, definitely. So more the country invests in science and there will be more people doing science. And then on the long term, we can also contribute more to the society and to the social economical growth as well. I really personally believe that through education, science, and technology, we can really fight poverty on the long term. I always say that. So, so funding is definitely another issue. And then nowadays, in astronomy at least, we have so many public data available, so you can do really good science, even if you don't have access to the infrastructure and observatories. Plus, it is much easier to get observational time than even on the international level than that it was previously. So I think giving the support to our colleagues to really contribute as much as possible into international initiatives and taking participation in international collaborations, either on a continental level or just the global level, is really very important. So opening different calls, forwarding the information, because there are also many calls that are where the funding can be obtained, not only through the national funding proposals and calls. There are different international proposals and calls that can be also used. So again, trying to bring the strong network is also very important, that we can forward the relevant information and also support each other. One of the things, for example, is also supporting each other in terms of lecturing, sharing the lecturing material and so on, so that people can stay more into the research as well. These are some of the points. There are others as well.
Yeah, I mainly wanted to raise this question because we're definitely going to upload this on YouTube, and a lot of people are going to see this, and I just wanted to, you know, like share that, to hear your insight on this perspective. So I think this is going to end our, we just got another question, so I think maybe we might want to take it. So it says, it's from Adonai Mulugeta, and it says, what is the energy source of an active galaxy?
Okay, so as I said, the principal energy source mechanism of nuclear activity is really the accretion of the material onto the supermassive black hole. So once again, you need to have the supermassive black hole in the center of the galaxy that, as I said previously, we basically have nowadays in all galaxies. But then you also need the material to be brought to that supermassive black hole, and then the accretion of that material. So once you have the material brought to the accretion disk and the accretion of the material, there will be a huge liberation of the due to the accretion of the gravitational energy that is then responsible for all these strong luminosities that we are observing. That would be, let's say, the simplified image. But now when you go to the emission that we are observing in different parts of the electromagnetic spectrum, let's say from X-rays to radio, we have different explanations for different emissions that we are observing. So the principal mechanism is the one that I mentioned, but then the emission but then, as I said in one of the slides, we have different components of the AGN. We have the supermassive black hole, the accretion disk, the obscuring torus, broad line region, narrow line region, and then in some cases the relativistic jets. No? So when you now want to explain in more details the emission in X-rays or in gamma rays, the emission in infrared, the emission in radio, and so on, or in optical, then we actually have to go much more into the details, into the structure of the AGN as a whole. So then you will see that X-ray emission will come more from the accretion disk, hot corona that we have around the accretion disk. If you go to the radio, you will get the radio emission is related with those relativistic jets that we mentioned, and then it will again depend on the properties and the strength of the magnetic field and the spinning of the black hole and so on. Then when you come to the optical infrared, you will depend also on the properties of the torus, of the obscuring torus, because basically the emission that is coming from the central part of the AGN will be absorbed by this gas and dust that is surrounding the central part of the AGN and then re-emitted in optical infrared and so on. So actually, the explanation is much more complex when now you try to go through different parts of the electromagnetic spectrum. And then, as I said, we are reflecting actually emission coming from different parts or different components of the AGN.
Okay, awesome. So I think we're all done with the questions. And Marianne, it was such a nice presentation that you gave us today, and we really appreciate all the time and the effort you put onto this webinar that we had for the past almost 2 hours now. And I would like to say thank you to all the participants that were with us together the whole time, and we're actually asking questions now and then. Yeah, so for the rest of the participants that are still online, stay tuned on our social media, Ethiopian Space Science Society, ESSS, and official ESSS. We will be available in all platforms. And additionally, we have launched this new ambassadorship program. So if you're under the age of 24, feel free to apply. And thank you. So Marianne, thank you again. It was such a really nice presentation. It's good to have you. Thank you very much.
Thank you very much once again for organizing. Thanks to all participants, and really once again thank you for all the amazing work that you are doing within ESSS, even in these really challenging times. So thank you. The privilege is really mine to be part of this society. Yes, so you can really count on me anytime you want.
For sure, we'll definitely reach out onto you anytime. Okay, so
good. Okay, see you soon.
See you soon. Yeah.
Bye. Bye.
Thank you.